Okay, in today's video I'm going to explain about isomerism in coordination compounds. Okay. This is everyone knows, I hope, that isomers are those compounds which have same molecular form number but different structures or different spatial arrangement. Okay, isomers are of two types. One is structural isomers and another one is stereoisomers. And in isomerism in coordination compounds, structural isomers are of mainly four types: ionizing isomers, linkage isomers, hydrate and coordination isomers. While stereoisomers are of two types: geometrical isomers and optical isomers. And this geometrical isomers are again of two types, which are cis and trans. And the basic difference between these structural isomers and stereoisomers is that the structural isomers will have different IUPAC names. Let me explain this in the following examples. And they will have different connectivities. And in case of stereoisomers, they will have same IUPAC names and the same connectivities, but they will have different positions of ligands in space. In isomerism in coordination compounds, different positions of ligands in space will be there. Okay, in stereoisomers. Okay, let me go to the next slide. In structural isomers, I'm going to explain about each types. The first one is ionization isomers. Ionization isomers are those isomers in which there is exchange of ions between coordination sphere and the ionization sphere. This is ionization sphere and this is coordination sphere. So when these complexes are dissolved in water, they will produce different ions. That is the basic difference or basic identification for ionizing isomers. For example, cobalt NH3 5Cl and the sulfate is a counter ion here. When this coordination compound is dissolved in water, this will produce a complex cation, which is pentamine chlorido cobalt 3 and a sulfate ion. Okay, and its ionizing isomer is obtained by exchanging these two ligands. Means sulfate ion will come inside the coordination sphere and the Cl will be the counter ion in this case. So when this coordination compound is dissolved in water, this will produce this complex cation, which is different from this cation and the chloride ion. In the first case, chloride ion is not obtained. Chloride ion is inside the coordination sphere, and so aqueous solution of this complex will not give the taste for chloride ion, because chloride ion does not ionize in this case, but it will give the taste for sulfate ion because it is ionized. Similarly, in this case, aqueous solution of this complex will not give the taste for sulfate ion because sulfate ion does not ionize here. Only chloride ion is ionized. So aqueous solution of this complex will give the taste for chloride ion, not for sulfate ion. Another example is this chromium NH3 5Cl and the Br. Here we will get its ionizing isomer by exchanging chlorine and the bromine. In this case, bromine is the counter ion, and in this case, chlorine is the counter ion. Okay, in the next type of structural isomer is hydrate isomers. This is the second type of um, structural isomers. In hydrate isomers, number of water molecules acting as ligands are different. For example, in this compound, which is a complex of cobalt, 3 Cl molecules are there and 6 water molecules are also present. Two important points about the complexes is that coordination number of cobalt must be 6 and oxidation number must be +3. So in each isomer these two conditions must be satisfied. So in the first possibility of hydrate isomer, cobalt and 3Cl molecule, 3Cl 3 chloride ion and 3 water molecules are inside the coordination sphere as secondary valency, and the 3 water molecules are present as hydrate. So so in this hydrate isomer, how many water molecules are acting as ligand? 3. In the second possibility, out of the 6 water molecules, 4 will act as ligand with 2 chloride ion, so that coordination number of cobalt is 6. This is to be followed, remember. And out of the 3 chloride ions, 2 are acting as ligands. The remaining one is present as the counter ion, and the remaining 2 water molecules are present as hydrate. In the third example, in the third possibility, 5 water molecules are acting as ligand with 1 chloride ion. So in this examples, number of water molecules acting as ligands are all different, so they will produce different colors. They will produce different colors in their aqueous solution also. These hydrate isomers, okay, these hydrate isomers will have different colors. Okay, now let me go to the third structural isomers, which is in this case linkage isomers. Now linkage isomers are those isomers in which ambidentate ligands are present. If ambidentate ligand is present, linkage isomerism is possible. If ambidentate ligand is not present, then linkage isomerism is not possible. Ambidentate ligands are CN or NC, ACN or NCS. This is cyanido, this is isocyanide, thiocyanate or isothiocyanate, NO2 minus NO2 or what, ONO. This is nitrito N and ONO is nitrito O. For example, this is an example of complex of chromium in which 5 ammonia molecules along with CN are acting as secondary valency or ligands. Here chromium is directly attached to carbon. This carbon is acting as donor atom here, because this carbon atom has a lone pair of electron. Similarly, its linkage isomer, the donor atom will be N, this N, so this will be isocyanide. Okay, this is cyanido, this is isocyanide. So these two are hydrate isomers, these two are linkage isomers. Similarly, we can give this example also, FeCl5 along with NO2, and its linkage isomer will be, here nitrogen will be the donor atom. Nitrogen will be the donor atom, and in its linkage isomer, ONO is the ligand here, and here the donor atom is oxygen, not here the donor atom is oxygen, not nitrogen. So NO2 is also a link, ambident ligand, therefore these two are linkage isomers. Similarly, we can give the example having this ACN and NCS as linkage isomers. The last type of structural isomers is coordination isomers. This coordination isomerism is possible only when both cation and anion are complexes. For example, in this case, platinum NH34, and this is the cationic part. Okay, this is the cationic part, and this is the anionic part. So both cation and anion are complexes here. So we can make coordination isomers by exchanging the ligands. If ammonia and the Cl are exchanges, then we will get these coordination isomers. Other than these coordinate isomers, we can make another isomer also. For example, platinum NH3 3. Here number of ammonia molecule is 4, but I am keeping here only 3. But one Cl will be exchanged with one ammonia molecule. So one Cl will come here, and in this case nickel will be there, and one ammonia molecule will come here from this coordination sphere, and 3 Cl molecule will be present here. This is also one coordination isomer of this complex. So similarly, we can make another coordination isomers also. So in these two examples, we can just assume that instead of saying exchange of ligands, we can just say for simplicity the exchange of the central metal. Platinum goes to the place of nickel, and nickel will come to the place of platinum. Actually, exchange of central metal does not take place. Exchange of ligands takes place. I'm just saying for simplicity. Okay, so these are the examples of structural isomers. Now let me go to the second type of isomers, which are called stereoisomers. This is of two types. One is geometrical isomers, and another one is optical isomers. Geometrical isomers, isomerism is possible in square planar complexes and octahedral complexes, and optical isomerism is mainly possible in octahedral complex. It is also possible in tetrahedral complex, but that is out of the syllabus in your standard. So first of all, let us consider about geometrical isomerism in square planar complexes. Okay, let me change the color here. Let me take black color. Okay, so here in this case I am giving some examples in which geometrical isomerism is possible or not possible. Okay, so in this type of square planar complexes in which only a single type of ligand is present, all the 4 ligands will be of one type. So, and another type is Ma3b. So in the first two complexes, geometrical isomerism is not possible. And Ma2b2 or Mx2y2, we can say, two types of ligands, each number of each ligand has to be 2, Ma2 B2. In such square planar complexes, geometrical isomerism is possible, and if the four ligands are all different, A, B, C, D, then also geometrical isomerism is possible. So let me give the example of this one first. This is a platinum complex in which two ammonia molecule and two chloride ions are present as ligands. Oxidation number of platinum in this case is +2. Okay, so this complex is called platin commonly, and I'm drawing its C's and the transforms. In the C's form, the two Cl molecule will be in the same side, while the two ammonia molecules are on the same side. We can keep Cl here and here also, ammonia here and here, no problem, as we like, but they must be in the same side, or they must be in 90° in the Cis form. And in the trans form, the ligands, similar ligand, or same ligands must be in opposite direction, that is, they must be at 180°. Ammonia must be at 180°. Then such geometrical isomer is called trans isomer. So this is cisplatin and this is transplatin, and one use of this cisplatin is that it is used as anti-cancer drug in the treatment of cancer in chemotherapy. Okay, next is this example in which all the four ligands are different. I'm taking this example in which ammonia, bromide, chloride and pyridine are acting as ligands. In this case also platinum has an oxidation state of +2. Okay, so such type of square planar complexes can have three geometrical isomers. How we can draw those three geometrical isomers is that we need to keep one of the four ligands in a fixed position. For example, I am keeping ammonia's position fixed in all the three geometrical isomers, and opposite to NH3 I am keeping bromine, and the second one I am keeping chlorine opposite to ammonia, and in the third one I am keeping pyridine in the opposite position of ammonia, and the remaining two positions can be occupied by the two remaining ligands. Here chlorine is there, pyridine, or I can put pyridine here and chlorine here, no problem. Okay, and in this case bromine and pyridine, or pyridine or bromine, and in the last one chlorine and bromine, or bromine or chlorine. So out of the three geometrical isomers, two will be cis forms and one will be trans form. Cis in the way that two halide ions are on the same side. Here also two halide ions are on the same side, therefore they will be regarded as cis isomers, while in the trans isomers the two halide ions are at 180°, so this will be treated as trans isomer. Okay, so there are another example for square planar complexes also. For example, we can keep this example also. We can give this example AA-2 in such square planar complexes. So generally this is M. In such square planar complex also geometrical isomerism is possible. Here AA is a bidentate ligand, but unsymmetrical bidentate ligand. Unsymmetrical bidentate ligand. Okay, so unsymmetrical, one example of unsymmetrical bidentate ligand is, we can give the example of glycine. As a ligand, this will be glycinato. This is the structure of glycine. CH2 COO minus and NH2. This is the formula for glycinato, or structure of glycinato. This can act as an unsymmetrical bidentate ligand. So in square planar complexes in which two glycinato ligand are attached to the central metal, and in such case we can draw the Cis transform. Okay, so but I'm not drawing that Cis transforms. Okay, so in the next geometrical isomerism is in octahedral complexes, and here I'm writing some examples in which geometrical isomerism is possible, and in some cases it is not possible. For example, in MA6, in octahedral complexes coordination number is 6, not 4. Okay, MA4, MA5B, in these two complexes we cannot draw the geometrical isomers. That is, no geometrical isomerism is possible in these two complexes. And possibilities there in this complex MA4B2, where A and B are unidentate ligands, monodentate ligands. Okay, and MA3B3. In this case we can draw Cis and trans, but in this case MA3B3 we mention the term facial and meridional in this case, not Cis and trans. Facial is just like Cis and meridional is just like trans. Okay, and in this case also MAA2B2, where AA is a bidentate ligand, symmetrical bidentate ligand. If this is unsymmetrical, then it has to be represented as AA dash. Okay, so example of bidentate symmetrical bidentate ligands are EN, ethylene diamine, and oxalato. Okay, and the fourth one in which geometrical isomerism is possible is such complexes in which all the 6 ligands are different. In such case 15 geometrical isomers are possible. Just remember this number only. You are not supposed to know all the 15 geometrical isomers in this case. Just know the number of geometrical isomers possible for such complex. Okay, let me give the example of this first. In the first example, MA4B2, here this is the complex. The first example is that of cobalt, in which 4 ammonia molecule and 2 chloride ions are present as ligands. So in the Cis form, the 2 Cl are on the same side, while 4 ammonia are on same side. So this will be Cis, and in trans isomer the 2 Cl will occupy the 2 axial position, or this 2 Cl can be in this position also, this and this, or this and this, no problem. You can draw whatever you like, but this is a good structure. And in the second example, I am giving the example in which 2 types of ligands are present, each of whose numbers are 3 each. Cobalt NH3, 3Cl3. So here I am drawing the facial isomer in which all the 3 NH3 molecule occupy the positions of a face of an octahedron, and these 3 Cl occupying in another face. So this will be called as facial or FAC in short form, while in meridional 2 Cl occupy the axial position, and the remaining 4 positions you can keep all the 3 ammonia molecules and 1 Cl wherever you like. Here ammonia can come and this Cl can come here also, no problem. This is meridional. In this case no cis trans isomer is mentioned. Instead of cis trans, the terms used are facial and meridional. Okay, let me go to the next example, in which 2 En molecules are present as ligands and 2 Cl ions are present. In the cis form, 2 Cl are on the same side, while 2 En are also on the same side. And in the trans form, 2 Cl are occupying the axial position, and the 2 En are also on opposite side. So this is the trans. Next type of isomer is optical isomer. In optical isomers, to show optical isomerism, the molecule or complex must rotate a plane polarized light. Okay, so optically active means the molecule is able to rotate the plane polarized light either clockwise or anti-clockwise. The complex which rotate plane polarized light towards means clockwise, this is given as the term dextrorotatory, and those complexes which rotate plane polarized light anti-clockwise, then those complexes are given the term liborotatory. Okay, this can be represented as plus also, and the liborotatory are represented by minus also. So in the theoretical way, to be optically active, the complex must be chiral. Chiral means the molecule must not contain any type of symmetry, means the molecule must be asymmetrical. So here I am giving some octahedral complexes which are optical active, and some are optically inactive. Suppose MA6, MA5B, MA4B2, in which geometrical isomerism was possible, but these complexes, either the cis or trans, they are not optically active. MA3B3, here also geometrical isomerism was there, but this complex is not optically active. And here I am giving 2 examples of octahedral complexes which are optically active. The first one is MAA2B2. AA is symmetrical bidentate ligand, for example En, and another example is MAA3. So let me draw the optical isomers of these 2 types. The first one is cobalt Cl2En2. This is let me keep the charge here of the complex. So such complexes are also geometrically active, transform and cis form. Remember, the transform is not optically active, because let me show here. This is the transform. Here in this complex, symmetry is present because this can be bisected equally, and the 2 halves will be exactly mirror images of each other, which means this complex possesses symmetry, plane of symmetry. So this since this complex possesses symmetry, this is not optically active, but this cis isomer is optically active. Okay, so I am drawing the cis isomer here. So suppose this is the mirror, and this will be its mirror image. Its mirror image is you know, Cl, 2Cl will be here, En, and this En is here. It is just its mirror image. So these two compounds, which are mirror images of each other, but they are independently optically active, they are called enantiomers. Definition of enantiomers is two optically active compounds which are mirror images of each other. They are called enantiomers. Okay, and a mixture of two enantiomers in equal ratio or proportion is called racemic mixture. It's called racemic mixture. Okay, remember, racemic mixture is not optically active. Racemic mixture is not optically active, but independently the two enantiomers are optically active, but the mixture is not optically active. Okay, in the last example I am drawing the enantiomers of this complex in which 3 En molecules are acting as ligand. These are the enantiomers of these complexes, mirror images of each other. Okay, I hope this is clear, and if you have any doubt, please write in the comment, and if you want me to make some video on some topic, please mention in the comment section. I'll definitely make video on that particular topic. Also, please like and share this video to your friends, and if you are new to the channel, please subscribe to the channel and also press the notification button. Thank you for today.